can see me from the front instead of the side. So here we go again. The Dosewallips watershed is outlined in blue here, and my map area intersecting it is that little rectangle. And so what I'm going to do is talk more or less from old to young, theme of the day, I guess. Bedrock and tectonics, then some thoughts about faults, glaciations, and some tidbits about post-glacial alluvial events and dynamics. So the geology of the Olympic Peninsula was summarized in 1978 by a compilation map by Tabor and Cady of the US Geological Survey. And more than 40 years later, this map really remains an outstanding reference for the geology of the Olympic Peninsula as a whole. Excuse me. The big picture here is that the Lilac Horseshoe is a rim of about 50 million year old or early Eocene crescent formation basaltic volcanic rock. Everything else is younger sedimentary rock in green and blue, and yellow quaternary sediment. I omitted a little bit of older rock that's exposed very locally in just a small part of the Olympic Peninsula. The crescent formation is part of the larger Silesia terrain of basaltic rocks found near the Pacific coast from Vancouver Island, that is, to southern Oregon around Roseburg. The precise origin has been the subject of much debate, but fundamentally, this is a basalt assemblage that was erupted in a mainly marine paleo environment. Lava deposition was partly subaerial as flows, and partly in contact with marine water, locally forming pillows, for which I don't recall seeing much evidence in this quadrangle. That is, I saw a few pillows here and there, but nearly all crescent basalt I saw in the Brennan quadrangle was from flows. Not necessarily subaerial. Some flows can also be submarine. Pillows are sort of they form when all the stars line up and the conditions are just right. You know, a lot of people think that basalt pillows are just the only way that you can tell if a flow was deposited in the marine setting. That's not actually the case. They are a special circumstance. It is reasonable to think that maybe a bit farther west in the Dosewallips watershed, the basalt turns more pillowy because that's where we get into more lower crest formation. And lower crescent formation and upper crescent formation are not necessarily older and younger. There's been much debate on that, but it is fairly widely acknowledged that the lower crescent formation, as just a facies of the overall unit, has more pillow basalt in it than the upper crescent formation. So here are some Hood Canal exposures along the shore for some basalt flows, very nicely colonnaded here. Notice that they dip a little bit. That is fairly typical, at least at the eastern end of the watershed, that the basalt dips a little bit towards the Puget Lowland, so east down. And that makes sense in the regional sense that there is a bedrock basin in the Puget Lowland, as opposed to the bedrock high in the Olympics. Most of the exposures are more massive, or their jointing is less obviously systematic. Ken Clark, pictured here, he's a professor at the University of Puget Sound, and cohorts have suggested that some flows in this area may be as much as 600 feet, or it might have even been 600 meters. I don't remember off the top of my head which of the two, but 600 something thick, and would therefore have to be the product of inflation. I don't think the part about the inflation is really published. He and I have talked about this at some length, and the summary of it is that if you have something 600 something thick and it's all basalt, then the extrusion rate to bring that out as one flow all at once without inflation is basically unheard of. Now, what does inflation mean? It means that you first put out a flow as a thin sheet, and before it is fully cooled, more lava squeezes into the center of the flow, thereby thickening it and elevating the flow top surface. This is a process that was first documented in Hawaii by one of the Cashman sisters. I believe it was Kathy Cashman. The Cashman sisters are a family of, I believe, 3 sisters, all geologists. Sue Cashman, I know, is a structural geologist. I believe Kathy was the volcanologist that observed this in Hawaii. So on a little bit to the tectonics of the Silesia terrain. Geochemistry can tell us something about the depositional setting and tectonics. Please pardon the fuzzy graphics and pay no attention to the colors here. The point is that everything except the yellow and red dots is crescent formation basalt from Western Washington. And that, geochemically, crescent basalt is one, mostly tholeiitic and ranges to calc-alkaline. And 2, plots between mid-ocean ridge basalt and ocean island basalt. So these are sort of end members of basalt characteristics that have tectonic implications. And it turns out that this stuff is somewhere in the middle. That's a little bit unusual. And some studies have suggested a link to the Yellowstone hotspot. Now, the Yellowstone hotspot at the time was thought to actually be off the coast of Oregon and Washington. So this is not as wild as at first it sounds. In 2014, Ray Wells and cohorts published a paper that suggested that 51 million years ago, Silesia as a terrain was situated west of the North American coast and a subduction front that was then farther inland than it is now. And that this terrain then stretched, as it does now, from Vancouver Island to the Klamath Mountains. Be that as may, the Silesia terrain was deposited between about 55 and 48 million years ago. We know that from a number of uranium-lead dates. Earlier dates were largely argon or argon, potassium argon, and were generally less precise and more susceptible to resetting, meaning that once the rock was formed, something happened to it and it reset the clock on the analysis of the date. So you get an artificially young date out of the rock. And that seemed to be a problem in this terrain. So the uranium lead got past that and it gave us a pretty solid picture now that the terrain as such is about 55 to 48 million years old, somewhat older in the south and a bit younger in the north. So here in Western Washington, we're looking at about 53 to 48 million years, I believe. Silesia is associated with thickening of young ocean floor at the time, in the left image, was presumably associated with that Yellowstone hotspot. So first we had run-of-the-mill subduction with ocean floor sliding underneath the continent. Then that Yellowstone hotspot started interfering and ended up thickening that oceanic crust. And that made it buoyant near the coast, thicker and overall harder to slide under the continent. So instead of sliding, it eventually got stuck, and in the geologic terminology, it got accreted to the continent. And the subduction faulting shifted farther west offshore, where now a thinner crust is being subducted west of Silesia. So the thickened crust that got stuck on the continent, that's what we now know as Silesia. And in Western Washington, Silesia is the crescent formation. What also was happening at the time, shortly after accretion anyway, sedimentary rock sediments were washed out from the Cascades, North Cascades particularly, offshore, what is now the Olympic Peninsula. And later mountain building is again associated with the ongoing subduction that now is causing some east-west compression here, that pushed the Olympics up and turned these sedimentary rocks into what's called an Olympic subduction complex, a sheared set of and slightly metamorphosed set of sedimentary rocks. And the cartoon on the bottom, I just couldn't resist putting that in there. The Northwest Geological Society is so privileged to have this wonderful tectonic setting in its backdrop, so I love that logo. The next segment of the talk, I want to talk about the rocks on the Olympic Peninsula specifically a little bit more, the core rocks, well, the sedimentary rocks. They're known as core rocks or Olympic subduction complex. And I don't actually know a whole lot about them. I haven't worked in areas where those are present or prominent, but suffice to say that the accretionary wedge sedimentary rocks that you saw in that cartoon a moment ago, the accretionary wedge being this business right here. Those are widely exposed in the center of the Olympic Peninsula, all that green stuff here, where they have been labeled core rocks or Olympic subduction complex. I don't know much about these because, again, my map areas have generally been too far east or north. Many of these sedimentary rocks have been metamorphosed at low temperatures, and in some cases at least high pressures, to what's known as the prehnite pompelliate facies. And that is something that Tabor and Katie's map mentioned at the beginning here really outlines quite nicely. The one thing I should note about the core rocks is that traditionally the crescent formation was thought to include at its base, so the inner side of its horseshoe, a unit known as the Blue Mountain unit, and that would be a mostly sedimentary rock facies of what was thought to be part of the crescent. Some of the more recent uranium lead age control generated by Mike Eddy and published in 2017 showed that the Blue Mountain unit is actually younger than the crescent basalt rocks and should therefore be associated with core rocks rather than the Silesia terrain. And that means, among other things, that there's a through-going fault that separates the core rocks from the Silesia terrain. By the way, the above image here is a clip from the Washington Geologic data portal. It's a website as shown here, and I would be happy to send that to anybody who wants the link. It's really a nice COVID-ready, powerful tool for finding geologic data and for that matter, generating your own custom map. You can put different backdrops underneath it. You can choose whether you want a street map or whether you want a geologic or a physiographic image like this. And you can turn whatever you have on the screen onto a PDF. You can scale it in and out. You can download particular data sets, say all the age control data of a particular kind. So a lot of versatility and a nice resource if you're looking for some geologic data. So on to the bedrock specifically in the Dosewallips watershed. The watershed captures pieces of both the sedimentary core rocks and the crescent terrain. And so what you find as bedload gravel in the Dosewallips is a bunch of sedimentary rocks as well as a bunch of basalt. And if memory serves me right, in the modern stream bed, we found a bit more sedimentary rock than basalt. Don't quote me on that. I don't have my notes from this project here at home. I'm working from home and our office is closed. So most of my project resources from almost 10 years ago are not actually at my fingertips. But as far as I recall, we found a little bit more sedimentary rock than basalt in the bedload. Anyway, I got a little bit off track here. So to sum up the bedrock story here, deposition of just to sum up, we first had emplacement and accretion of the Silesia basaltic terrain. That was followed by deposition of sediment that washed seaward from the continent out offshore of Silesia. And that in turn was followed by crustal shortening, where east-west compression led to mountain building that then cut off that sediment supply and started mangling these sedimentary rocks, as well as the Silesia volcanic rocks. So the subduction-inspired crustal shortening uplifted the Olympics, deformed the rocks throughout, and as a result, we now have mountains that stand in the way of wet marine air blowing on shore, which led to formation of a bunch of rivers. Among these, the Dosewallips watershed is moderately sized. For instance, the Elba is maybe twice as big. It drains the east side of the Olympic Mountains eastward into Hood Canal, and the watershed drains areas covered with both silesia and sedimentary core rocks. It lacks dams and other major development, and except for patchy veneers of glacial sediment, it's pretty much home to clean, if mostly somewhat altered bedrock. So much of the river is hard to get to, so only a few really challenged characters like geologists ever mess with it. And it probably provides some wonderful fish habitat, except maybe for the nick points. And those nick points might have something to do with geology. So some thoughts about faults and uplifts. The Olympic Peninsula is home to a number of mapped faults. This is, again, just sort of generated by the portal, including some thrusts within Dosewallips watershed. So thrust faults here are displayed as these black lines that have little triangles hanging off of them. And the triangles just tell you that that side was shoved over top of the other side. Again, the fault that separates Silesia from the core rocks is not identified as a through-going fault on here yet. Sometime in the future, I hope that we will get that done, but it hasn't been mapped out yet. And who knows when somebody is actually going to go and map all this. So there are plenty of faults known in the Olympic Peninsula. Fault activity levels are mostly unassessed. The tectonic setting is active and compatible with many of the map faults, and some are active. For instance, the Lake Creek Boundary Creek fault system out here. The Saddle Mountain fault system out this way, actually through here. We know those are active. There are clearly also some respectable faults not shown here within and near the Brennan quadrangle. For instance, the Seattle fault is only partly shown through here. So there may be more fault activity than meets the eye, even from that general map of known faults. For instance, when we were mapping the Brennan quadrangle, we found occasional fault exposures in somewhere in the forest roads that had no known association with any faults. These are two images of such fault exposures, fairly respectable. All this right here is fault gouge. These did not lead to mapping of faults beyond the particular exposures because we were unable to trace these faults from one exposure to the next. So we couldn't establish where they went, how big they were, or whether they were modern actors. That's just an illustration that much remains to be learned in this neighborhood. At least some faults nearby are quaternary active. If you look at, okay, that was not somebody trying to talk with me. If you look at this image, you can see how the bedding here is offset several times. Oops, pardon me. And really what's going on here is that the left side of the image is being lifted over the right side of the image and slid to the right into the rocks on that side. So the rock scattered here, or shattered, and broke in all these little bits. Now, this particular exposure is from the Tuandos Peninsula, roughly here. So just across the water from the Dosewallips. And it's not actually bedrock. These are quaternary sediments. They look a bit like bedrock in this picture, but they're really just sandy to silty sediment. and with that, we know that it is a relatively recent activity. The person standing in the middle here is Trevor Contreras, who headed up mapping of that particular area when they bumped into that particular exposure. Other known post-glacial activity includes on the Seattle Fault, so that would be through here, across the Puget Lowland, the North Olympic Fault Zone.
Excuse me, Michael.
So, yes?
I'm not sure about everybody else, but I'm having trouble seeing your cursor or the map that you're referencing. I just see the image with the...
Oh, I'm sorry. Yes. I was pointing at the next slide, which doesn't help you guys. Sorry about that. So the Seattle Fault across the Puget Lowland, that's clearly known to be post-glacially active. The Northern Olympic Fault, or the combination of the Lake Creek, Boundary Creek, and Sadie Creek faults, and then the Saddle Mountain Fault Zone, or Saddle Mountain East and West faults, including a couple of other named faults farther southwest that are all part of the same beast. The Tacoma Fault, all these are known to be active. There's probably more going on in here. There seems to be a small fault or a local fault going across the Skokomish Delta. So there's quite a bit of fault activity in the neighborhood. The Olympic Peninsula is actively uplifting to the tune of about 2 millimeters per year, according to Tammy's notes from your last meeting. That rate may be based on more recent work than what I am showing here. I've not looked into it lately. This figure is from a master's thesis by Jessica Hellwig in 2010, and she based it on a paper by Brandon and others in 1998. Suffice to say that with this ongoing uplift and in light of the active Cascadia subduction zone and a regional pattern of north-south crustal shortening across Washington, it is a pretty safe bet that the Olympic Peninsula has its share of active faults, even if it remains largely unclear which of the many unrecognized and recognized faults on the peninsula are in fact active today. And with that, let's move on to glaciation. The Olympic uplift throughout the past several million years has led to an orographic barrier that receives lots of moisture from wet marine air blowing on shore. This image, also from Jessica Hellwig's thesis, shows historic precipitation patterns across the Olympic Peninsula in meters per year. So, where it's red, we have about 5 meters per year of precipitation, and blue, 0 to 2 meters per year. The pattern is fundamentally orographic, i.e. driven by topography, which is contoured in black in this image. And I find that a little bit hard to follow. We'll have a similar image here in a minute that makes that a little bit more accessible. Note that most of the precipitation is on the west side of the peninsula, i.e. west of the Elwha River. Presumably that's simply because the western areas get the first crack at getting wet. Olympic glacier development appears to be mainly driven by precipitation, that its temperature is less important than where along the west coast the jet stream blows in. So here's essentially the same precipitation image, but over LiDAR so that you can see the topography a little bit better. And again, here's the Brennan Quad and the Dosewallips watershed. And so this line here is a line of a section or transect in the next image. And the take home here is that the eastern third crosses the Dosewallips watershed headwaters. The data source for this image was mean annual precipitation data from circa 2012 DNR GIS. And it represents about a 100-year record of precipitation, according to the Oregon State University Prism Group. So this graphic is again from the 2010 master's thesis by Jessica Hellwig. And what it shows you, the blue line is the topographic transect across that line, or along that line that we had in the last image. The colored lines across the top are estimates of the equilibrium line altitude, or the ELA. And what that stands for is simply that above that elevation, we expect glaciers to build ice, and below that elevations, we expect glaciers to mostly melt. So there's a couple of different iterations of studies through the historic period that assess that line or that elevation across the Olympic Peninsula. And then there's one that does the same thing for the Pleistocene, meaning sometime before the last glaciation, and up to 1.6 million years ago. And it's not clear to me when during the Pleistocene, but suffice to say that what it showed is that at some point earlier on, the glaciers went much, much farther west down the slopes than they do now. Not much difference apparent on the east side of the Olympics. It seems like the top of the watershed was glaciated, but there's not much indication that ice accumulated at lower elevations. That doesn't mean that an ice train or an ice lobe couldn't have flowed down the valley a lot farther. It might have. So this kind of puts that out in space. You know, the black dots here are just places where there's now ice on the Olympics, and the red dots here are the farthest western extent of those ice advances according to the Pleistocene record. And these are from geologic deposits that people have mapped on the west side of the Olympics. And to put that a slightly different way one more time, so this is a model that Jessica Hellwig did for ice extent, and she really calibrated that with the geologic exposures on the west side, showing or predicting how far the ice would have moved. And that then also allows us to get a sense of what it likely did elsewhere on the Olympic Peninsula. And so for the Dosewallips area, it actually does predict that there might have been some ice that came all the way down to the mouth of the Dosewallips at Hood Canal. Not building ice, but just flowing that far down the slope. There hasn't been much mapping of the glacial extent on the east side of the Olympics. Partly that's probably just on account of access. Partly that's because good exposures have been hard to find. And partly it may be simply a reflection of the fact that there's not as much glaciation as there was on the west side. We don't necessarily know what's the answer there, but so far finding good glacial records on the east side of the Olympics has eluded us. What is clear is that voluminous Olympic sourced gravel packages were deposited east of Hood Canal, so on the Kitsap Peninsula, the western Kitsap Peninsula at least. We find large blocks of gravel. There's also some exposures that might be till out there. I wouldn't necessarily want to hang my hat on the notion that any of those were as far as the ice got, but it's possible. And it would be in line with the modeling here showing the ice at least going into Hood Canal. But the gravel packages do tell us that Hood Canal wasn't always there. Sometime before the last ice age, gravel washed from the Dosewallips all the way out to about here. And if you think that there wasn't a Hood Canal, it's an open question whether the ancestral Dosewallips and Duckabush would have flowed and how they would have eventually gotten their water to the ocean. They might have done something way convoluted, maybe going all the way around. So what do we actually know about glaciation in the Dosewallips Valley? The pictures on the left here show two sort of end members of valley forms. The upper one is how ice carves valleys, and the lower one is how water carves valleys. So there's a U shape for ice and a V shape for water. And I pilfered these images from a BBC website. And the image on the right here, pardon me, is simply a view from Hood Canal into the Olympics. I want to say this shows the Dosewallips. I'm not sure if it was the Duckabush or the Dosewallips. And again, I apologize, most of my notes are not with me, so I couldn't actually verify which watershed we're looking at. But as best I remember, both watersheds shared, at least to some extent, that sort of valley form, where it's much more U-shaped than V-shaped, suggesting strongly that these are ice-formed valley shapes. There is a complication with glaciation in the Dosewallips River Valley. Ice came at times out of the Olympics and at times out of the north from the Cordilleran ice sheet from Canada. In both cases, ice entered the Dosewallips Valley. By the way, the image backdrop here is a combined water and land digital elevation model that David Finlayson developed in 2005. So for the Cordilleran ice, here's the big picture. The Cordilleran ice sheet is an Arctic polar ice cap in northwestern North America. And during global glaciations, the Cordilleran ice sheet grew large enough that its southern ice front entered the Fraser Valley and then the Puget Lowland. And it went as far south as Tenino. Yeah, enough of that. Irrespective of where the ice came from, glacial ice definitely left its footprint in the Dosewallips River Valley. Scour and sediments, bedrock scour and sedimentary deposits. The ice scratched and polished the rock. You can see the striations in the lower right here. This ensured that most of the rock exposures are largely unweathered, at least below 3,000 feet. The ice doesn't seem to have risen above 3,000 feet at or near the area of Hood Canal. Again, I don't know really much about farther west in the core of the Olympics, but close to the Puget Lowland, about 3,000 feet was the maximum ice elevation. So above that, we find some deeply weathered rocks and soils. But below that, it's pretty clean rock. And plastered on top of it is commonly some glacial deposits. The ice movement sculpted the rock, leaving behind some broadly smoothed rock surfaces. And the striations and grooves here tell us which way the ice moved. It moved along that vector. What we most of the time cannot tell is which direction did it move. Every once in a while we get lucky and we get some telltale sign, but most exposures we don't. So we end up looking at the glacial deposits to get a sense of where the ice actually came from. And lucky for us, even though most of the rocks are pretty similar, we have a lot of basalt and we have a lot of sedimentary rocks out of both the Olympic Mountains and the Cordilleran ice. But what the Cordilleran ice brings in addition are granitic rocks and high-grade metamorphic rocks, both of which we do not find in the Olympics. So when the glacial deposits include a notable or readily apparent fraction of granitic rocks and high-grade metamorphics, we know that the ice came from the north. There's some mixing where some of the northern source rocks probably got washed into the Dosewallips River and then got moved again by things coming from farther up in the valley. So just because we have one granitic rock doesn't necessarily mean that we know for sure which way it came. But if we keep finding granitic rocks and high-grade metamorphics, we have a pretty good sense that this is associated with northern ice. And conversely, if we don't find them, it should have been something out of the Olympics. Based partly, at least, on this lithologic distinction, Friskin in 1965 in a master's thesis concluded that alpine ice at one point came most of the way down the valley to about here. And he noted brown oxidized compact sandy till and cemented sand and gravel about 115 feet above the Dosewallips River in the southwest quarter, section 24, township 26, range 3 west, and appears to be of Olympic origin. So that's how he described it, as the farthest downstream end of where he thought he saw evidence of Olympic ice. Cordilleran ice in turn bulldozed its way upriver from the east. And Friskin noted there that the westernmost observed granitic float in the Dosewallips Valley is 5.5 miles up the Dosewallips Valley. And he has a figure in his thesis that shows that more exactly.
Hi, Michael.
Yes.
We're still having trouble seeing your cursor, so are you...
Does it just kind of go in and out? See it now? Don't see it now?
Don't see it. I'm just wondering.
See it?
That extent of the ice, was it to the tip of that green arrow? That's...
Yes. So the green arrow is the Olympic ice. The blue arrow is the Cordilleran ice.
Does anybody see the cursor?
No.
And you don't see it now either?
We live without it, but if you...
Do you see it now?
Yes.
Yeah.
Yes.
I see. All right. So it remains debatable whether the two ice slopes ever actually met. They're not obviously in sync. That is, they're not obviously coming out at the same time. Olympic Mountain's ice build appears to be mostly driven by precipitation, not temperature, so it may have advanced at a different time. And we see that in the climatic record. Now in this fairly complex diagram, the blue bar, well, first off, the left axis here is time, with the present starting here, and then it gets progressively older down the line in 100,000s of years. So 20,000 years ago, we have a blue bar, and that blue bar marks the last time Cordilleran ice entered the Puget Lowland, the last glaciation known as the Vashon. And these stages here are marine oxygen isotope stages. So stage 2 was the last glaciation. Stage 4 is the one before that. Globally, both of these are combined into one broader glaciation, but 2 and 4 are the times when ice actually reached the Puget Lowland. And then 5B, 5D, as far as we know, did not enter the Puget Lowland. The next time that we know ice entering the Puget Lowland was stage 6, so more than 130,000 years ago. But suffice to say that globally, those blue bars are when the world was in ice ages. And when you compare that to what we get out of the Olympics, and this was compiled by Amy Staley, the master's thesis, or a master's thesis in 2015, what's becoming apparent is that there's a lot of glaciation in the Olympics, alpine glaciation, that was simply at different times. It's not in sync, and not a lot of glaciation during some of the global ice advances. More than that, and not really apparent from this picture, is that these glaciations in the Olympics that were not in sync with global glaciations were some of the most extensive in the Olympics. And with that, let's go on to glacial advance and pre-Vashon glacial deposits. We know that, well, the exact timing and extent of the alpine ice advances out of the Olympics remains speculative, but we do know that the Cordilleran ice invaded the Dosewallips Valley when the ice last invaded the Dosewallips Valley. And we know that fairly exactly on account of something we found in Rocky Brook, the northern tributary of the lower Dosewallips here. Roughly in this neighborhood here, we found some wood in lake sediment that was dammed by approaching Cordilleran ice. So what that meant is we had an exposure of mostly sand, a little bit of silt, and some pea gravel that was nicely bedded, and all those black dots in it are organic fragments, detrital pieces of wood and delicate organic matter. Some of the sedimentary structures in here told us that there was paleocurrent, at least some of the time, heading from left to right. And in this case, that means that paleocurrent was heading upstream. So there was something that had dammed the valley from downstream and was sending water upstream, at least at times. And it was flushing organic material into what then had turned into a lake. So we got a radiocarbon date on this, and it ended up showing us that this deposit here is between 17.8 and 17.5 thousand years old. The exposure is at about 1,350 feet altitude. And so we know from that at that time, 17.5 to 17.8 thousand years ago, the ice in the Puget Lowland at the latitude of the Dosewallips had reached a thickness high enough to block the Dosewallips River to 1,350 feet. If we look at the ice heading into the Puget Lowland, we know from the full glacial conditions, this is a graphic that, again, is from the 2010 Jessica Helwig master's thesis. The ice thickness at the maximum ice extent was about 1,000 meters at the latitude of the Dosewallips. So when that ice had gotten into the Dosewallips River and Rocky Brook only to 1,350 feet, we know that it wasn't at its maximum extent yet. Plus, somewhere above the exposure that we had here, we also saw glacial till. So that tells us something about when the ice invaded the Puget Lowland. Now, this is not the only place where we have some age control on that. Long before our mapping in the Dosewallips Valley, Steve Porter and Terry Swanson published a paper in 1998 in which they estimated the timing of the advance and retreat of the Vashon ice into the Puget Lowland based on some radiocarbon dates here at the latitude of Bellevue and at a place called Lake Carpenter. So by that age control, they simply said, okay, it got to this latitude about 17,600 years ago, and it had retreated again by about 16,500 years ago. So it got to Tenino somewhere in between. So they simply extrapolated like this. Since then, a lot more data has become available, such as what we had at Rocky Brooks. Pardon the clutter on this diagram. This basically here is the graphic from Porter and Swanson. All these colored bar graphs are points of age control at various latitudes. So the one at Rocky Brooks that we had was out here. The arrow on this end simply suggests where the ice front was relative to the particular age control location. Our sample was at 1,350 feet, and therefore we assumed a slope of the ice ahead of that is south of it, farther south into the Puget Lowland, and we said, okay, the ice was probably this far south at that time. And similarly, some of the other points here point a little bit farther south because they were at some higher elevations. Others were pretty much at ground level nowadays. Long story short, the revisions suggest that the ice got to its southern maximum a bit later than what Porter and Swanson had suggested. And indeed, their age control for post-glacially ice-free conditions at Lake Carpenter is problematic in light of a whole bunch of other age control from farther south. The blue ones here, the lower ones for sure, and maybe even that one, constrain when the ice was moving into the Puget Lowland, not when it was going back out. This one probably constrains when it was going out. And the message seems to be that the ice moved in gradually and then fell apart almost instantaneously from Tenino all the way to Port Townsend. The timing of all this is relevant because it tells us something about, for instance, post-glacial activity on faults in the Puget Lowland. When somebody finds a fault in the Puget Lowland and they find some record of earthquakes, the way we geologists calculate how active that fault is we document how many earthquakes we can find. And most of the time, the ones that are easy to document are those that happen after the last glaciation. So if there's 3 events since the end of the glaciation, if that end of the glaciation was 15,000 years ago, then that means every 5,000 years this fault can be expected to rupture. But if instead it's 5, we've got a lot more active. So if the ice got to the south later, that means that these faults are all a bit more active than if the ice got there sooner. And for that reason, this kind of business is actually sort of real world consequential. Anyway, what did all this tell us? What did all this do to the Dosewallips watershed? Beyond the U-shaped valley form, consider first what happens at the snout of a glacier. Meltwater and surface water carry sediment, coarse stuff drops out first. So here we have an apron of relatively coarse stuff, mostly gravel, some sand, and it usually forms braided outwash surfaces. Where confined in a valley, those form what's called a valley train, a smooth surface of braided deposits. And where it opens up, they tend to form a fan. Farther out offshore, or farther out away from the ice, it becomes progressively finer, particularly when gradients lessen, or when you get to a water body, then you end up with sand and silt and rock flour that can also be clay sized. So the expectation as the ice invades the Puget Lowland from Canada is that at some point the ice is going to get to the Olympic mountain front. And once it gets there, it hits this 5,000 foot high wall and turns that into a dam. And it fills the Puget Lowland south of the ice front with whatever meltwater came out of the ice and whatever river water flowed out of the Olympics and the Cascades. So suddenly Seattle to Olympia is a bathtub. And that bathtub no longer spills out through the Strait of Juan de Fuca, but instead is forced out to the south through the Chehalis River. And in that bathtub, we would expect at first distal lacustrine sediments, lake sediments, silt and clay. And then as the ice got closer, eventually there'd be some sand and then some gravel. And finally, once the ice is actually there, it would deposit some till, or a mix of all kinds of grain sizes. And we can indeed see little bits and pieces of each of these sediment facies in and near the Dosewallips Valley. Advanced outwash sediments, silt, clay, and again, when the ice was closer, sand and gravel are fairly common, not usually very thick. What you see on the right of this image is about as thick as we've seen it anywhere in the neighborhood. This, I believe, was just upstream of the Dosewallips State Park on the southern valley wall. And we have a succession of, what I want to say maybe in the order of 80 feet or so of silt mostly, and some clay and sand. And then at the top, there's a little bit of sand. All of this is, we can't see it here, but it's overlain by glacial till. So it's nicely compacted by the weight of overriding ice, and that is one of the hallmarks of advanced outwash deposits, that they are compacted once the ice got there because the ice just squeezes down on it. And again, our radiocarbon site was another example of that sort of thing. Similar sediments are exposed at Quatsa Point, southeast of the Dosewallips River mouth. So there's this peninsula between the Dosewallips and Duckabush rivers, and that's Quatsa Point. And when you look at the sediments that are exposed in the shore, above the shore of that peninsula, you can see quite a bit of similar sediment. On the Duckabush Valley side of it, on the south limb of that peninsula, we have these uniformly planar bedded east dipping sand and gravel sheets. Those are what we think of as foreset beds, meaning we think a river spilled into a lake there. At the top, we've got some horizontal bedding. Now, it's not clear that that was in this particular instance necessarily associated with the river that spilled this. In most delta settings, it is. But anyway, we could follow these dipping delta beds around the tip of the peninsula, and they eventually look flat where the shore heads north-south, not necessarily because they have turned flat, in some places they have, but because instead of looking at a slice where the river's on the left and the lake is on the right, we are now looking at a slice where left to right is the same part of that delta front. So if we went into the outcrop here, if we cut a big trench in here, then each of these beds would no longer be dipping at us. It would be a horizontal bed across. And that's what we're seeing out here. So in this particular case, we also ended up wondering, well, is this from the Vashon glaciation, the most recent ice advance into the Puget Lowland, or is this maybe older? And just from looking at it, we couldn't tell. So we tried finding out with what's called a luminescence age estimate. And luminescence is a pretty esoteric technique. Suffice to say that it has to be sampled in the dark or it doesn't work. And that made the whole thing fun. As you can see, we were holding a jacket up against the cliff here in order to keep light from coming in. One of us had their head under the jacket while they were trying to close the sample tube. And then later on, we were packaging the sample tube again in the dark in the holding well of the boat. But anyway, suffice to say that what we got out of that age estimate was that it was about 20 to 60,000 years old. That unfortunately was too fuzzy to be useful. That could be 20,000 years, pretty much the last ice advance, or it could be 60,000 years, the one before that. We're reasonably convinced that it was associated with some ice advance for a variety of reasons having nothing to do with the age control sample as such. So sometimes that's how it goes. You don't get the answer as precisely as you were hoping. So what else are we getting from the full glacial conditions and from the ice recession in the Dosewallips River? Once the Cordilleran ice had fully invaded the area, I would picture the lower Dosewallips River Valley looking something close to this, except with the ice surface dropping up valley and either impounding an ice-damped lake up valley or meeting an alpine glacier. Now, the alpine glacier would itself have looked very much like this picture. What sediment would a glacier leave behind in the valley? So if you look at the margin here, you can see that there's all kinds of debris that ravels down onto the edge of the ice. And at times, you also have water coming down, and that water is going to collect here and run down. Every once in a while, it might pond locally. So there's going to be a mechanism here for some sedimentation and maybe even some benches forming if that glacier is stable at that elevation for a little bit. At the bottom of the ice would be scoured and grooved bedrock and maybe also some lodgement till, which we already saw earlier in the picture, and we'll have another one here in a minute. Yeah, enough of that. So here's a picture of just some lodgement till that I believe was in the lower Dosewallips River. We were lucky on our project. We had the assistance of Ryan Gold, a Forest Service employee who also happens to be a geologist and a world-class adventure kayaker. And he was not scared to go over whatever waterfalls were in the Dosewallips or Duckabush rivers. So we put him in a kayak and sent him down the stream, and he looked at whatever rocks he could find along the channel that nobody else gets to see. So here was one of his kayak buddies staring at some till in what I think was the lower Dosewallips River. And you know, on that till, till is simply a mix of particles of all sizes. You know, it could be down to cabin-sized boulders, clay, silt, sand, all ground into place by ice. So in this case, it's fairly compact. In an exposure like this, it can act and feel a lot like concrete. So that's what's going to happen at the bottom of the ice. Now at the margins, you know, when we think of that glacier image a moment ago, you know, especially when it starts melting, we're going to get some streams braiding along the sides. We might get some meltwater inside the ice or at the bottom of the ice, and that also might deposit some things beneath the ice or in the ice. And as the ice melts, you know, those deposits are going to come out and form these snake-like river deposits that we know as eskers, or occasionally maybe some ponded areas come out as what we know as kames. And then on the sides, again, where we had a bunch of dirt and maybe some streams running down along the sides, we might find entire terraces that we know as kame terrace. And so with that, let's look a little bit at outwash terraces, lakes, shorelines, and implications of those features in the area. This is a LiDAR image, pardon the deep red here. The color really is just about elevation. And the blue is low elevation near sea level here. The red is elevation above about 165 feet. Blue was below 100 feet, so it's not just sea level. And the reason I scrunched that rainbow in between to that tight interval is that I really wanted to draw out the terraces that we see between 100 and 165 feet elevation here. This is an image of the lower Duckabush River. And I picked on that simply because it's a little bit more illustrative of that set of terraces, although a similar set of terraces is present in the Dosewallips. Notice that we go from 165 feet to about 100 feet across this length of the river. And for the modern river, we have about 15 feet less elevation drop. And that's fairly typical. The glacial or the proglacial environment tends to be very dynamic, lots of sediment moving around, and valley floors are commonly a bit steeper in the glacial environment. So these what are now terraces perched on the side at the time were valley floors. And at the front of it, there are deltas spilling out into a lake. And that in turn is something that is better visible in the Dosewallips Valley. So here's a fundamentally similar LiDAR image of the Dosewallips Valley. And again, we have a pretty broad terrace set at the bottom of the valley here. And then we have little bits and pieces of terraces. This one here is steeper and lower. It's a different iteration of terracing. But this piece, that piece, that piece, and all of this all used to be one valley floor. And in this case out here, it gives us a very clear image of a river again spilling out into a lake. This is what we know as the Brinnon Delta. Pardon me. This was, I forgot I had that slide in here. This was just the same area as that prior LiDAR image, now with geologic units drawn in it. So this is just a clip from our map. But suffice to say that at the snout of it, or at the downstream end, we have this Brinnon Delta that you've probably all seen from Highway 101 at the north end of Brinnon, where we have these uniformly dipping sheets of sand and gravel. And then at the top, we have horizontally bedded sand and gravel, river bottom sediments, or river, well, sometimes river marginal, but sometimes river bottom, but river bed sediments that are essentially horizontal. And so what we had was a stream going out into a lake, and it started a little bit farther upstream. And as it kept pushing sediment out into the lake, that lake slowly started filling in. And we ended up with that surface planed off by the river surface. So one thing that it does is it tells us how high the lake level was. And in this case, I want to say that was in the order of 120 feet, I believe. I thought I had that in the notes. Maybe I don't. Yes, I do. 120 feet is, so right out about here, the elevation is about 120 feet above sea level. Pardon me, that was not intended. And so we interpret this inferred lake back at that time as an ice-dammed lake that filled Hood Canal during the glaciation, or late in the glaciation. We think it's late in the glaciation because the surface over here is preserved, wasn't scoured out by the ice, and the deposits in here are not compacted by the weight of ice. So all of this must have happened after the last time that ice was here. So why was there a lake? Well, just because the ice had melted in the Dosewallips River Valley doesn't mean that it had melted everywhere in the Puget Lowland, and there could still have been enough ice elsewhere to form a topographic barrier that ponded ice in what is now Hood Canal. So we find that sort of feature in a number of places along the along the eastern Olympic mountain front above Hood Canal. And when we look at where all we find these kinds of things, we can put together the lake level up and down the Hood Canal shore. And it's not just deltas like this, it's also shoreline deposits, little bumps that ring the mountain front at the same elevation for some distance. Some of these are fairly subtle, but suffice to say that we found a number of points where we were confident we had some lake associated deposits or lake associated landforms. And the same sort of thing was true much farther south in the Hoodsport to Dosewallips, to Skokomish Valley River area. And all up and down the shore of Hood Canal, so from the southern end at the Skokomish River Valley at where Purdy Canyon climbs out of the Skokomish Valley into the uplands towards Shelton. That is, Highway 101 goes up Purdy Canyon there. From that latitude on north, we found a cluster of shoreline points near Hoodsport and the Skokomish Valley, and then we found another cluster near the Brinnon area. Now, regionally, Jerry Thorson in 1981 had a PhD thesis and a follow-up paper in 1989, and basically what he documented that throughout the Puget Lowland, there are points that tell us about old lake levels, and they have a regional slope to those. That regional slope makes sense if you understand what glaciers do to the earth. So when the glacier ice invaded the Puget Lowland, when you had more than 3,000 feet of ice, there's a bit of weight on the crust, and that weight causes the crust to subside. So there's a bending of the crust beneath the glacial ice. And when the ice starts melting and you have ice-dammed lakes, those lakes are going to form a horizontal lakeshore. And then later on, once all the ice is gone, that weight is no longer there, so the crust bounces back up. And with it, the old shoreline points bounce up. And so the thicker the ice, the more the crust bounces back up. So the farther north we go, the thicker the ice was. Therefore, the farther north we go, the higher those shoreline features get uplifted. That's what we're seeing in this graphic. At the south end, we have one elevation, and regionally going north, there's some slope where the ice just gets thicker, and therefore the shoreline features get higher up. And so here in the Dosewallips and Duckabush area, we had a line of pretty nicely lined up shoreline features that we can extend south to the south end of Hood Canal. And then we had a lower set, and there were more points available than we show here. We just didn't bother recording all of them because the picture was pretty clear. Suffice to say that in the Brynin and Duckabush area, yeah, we have two well preserved shoreline elevations showing us that there were two lake levels in succession. First a higher lake, then a lower lake. And that higher lake, when we take that slope and we extrapolate it south, we get to some place that is below the top of the hills at the south side of the Skokomish Valley. When Thorson and before him Bretz thought about the neighborhood, they thought that there was an ice-dammed lake in Hood Canal that drained out where Highway 101 now climbs out of the Hood Canal Basin onto the uplands towards Shelton. And they had going for them that there's a nice set of braided river channels in the landscape up there. But what they didn't know is that the shorelines of these lakes don't actually line up with that. You know, the ones around Brynin clearly point to a lower elevation, and the ones in the Skokomish Valley to Hoodsport area point at a different elevation, also lower and a much messier set. So what we're getting out of this, to my mind, what this probably is a tectonic signal. It tells me that the Brynin to Duckabush area is not offset by faults or not meaningfully offset by faults internally, but there's something tectonic that happens between there and the latitude of Hoodsport, where the Hoodsport area is uplifted relative to the Brynin area. This could be something to do with the Seattle Fault. It could be something to do with the Tacoma Fault. It could be something to do with the Saddle Mountain East and West faulting and other local structures in the, or closer to the Hoodsport area. And the fact that the Hoodsport area itself at any one latitude only shows us one shoreline marker, but they're all at different elevations here. That messy signal suggests to me that that area is internally disrupted by some deformation. So I would love to see quite a bit more detailed structural mapping happening around the Hoodsport area, because I think there's a story that hasn't been untangled in that neighborhood. With that, let's go on to the last bit, just some Holocene item here. One of the things that we stumbled into, and this was Ryan, Ryan Gold, the Forest Service employee that was kayaking, somewhere along the Dosewallips River shores, he found an exposure of some soft silt that was just full of charcoal bits. And so he grabbed a bunch of those, and it turned out when we got radiocarbon ages on those, that they were about 4,500 years old. As such, it tells us that there's a record of valley floor level changes in the lower Dosewallips that is in the order of 5 to 7 meters and no more than 5,000 years ago. So here's a picture of the sediment that he saw. Yeah, above that is some channel sand and gravel up to the top, and then there's a river terrace, which on the map is shown by this little platform. That's the only remnant that we recognized of that elevated valley floor. But it tells us that at some point during the mid-Holocene, the entire valley floor was that high, at least across that part of the valley. What could have caused this? Well, you can think of a couple of different ways of getting there. Our sort of favorite interpretation during the mapping was that it was a post-fire sediment pulse. And note in that context that a fellow by the name of, I think it was Brian, but anyway, his last name was Garcia. He had a thesis in 1996 speculating about some tectonic events in the Dosewallips basin. He had found west of our Brinnon quadrangle a similar sort of relict terrace, and gotten a radiocarbon date of 3,570 plus minus 60, and our age was 4,140 plus minus 30, and these are radiocarbon years. When you actually convert our age to calendar years, it could be between 4.82 to 4.57 thousand years, or between 4.56 to 4.55, or between 4.54 and 4.53 thousand years old. And that's just one of the vagaries of radiocarbon. It always needs to be converted into calendar years. And I haven't done that for Garcia's age, but suffice to say, his age seems to be close enough to where it's geologically reasonable that maybe his elevated terrace is the same signal as ours. And if we get a fire motivated pulse of sediment, fine sediment particularly, moving its way down the river, that might make some sense. Subtext, if there's a large fire somewhere in the headwaters, we might be in for some fairly drastic effects downstream over time, over a period of decades to perhaps centuries. Alternatively, there might have been a landslide that dammed some part of the lower valley and would have led to temporary aggradation of the valley floor upstream of the landslide. Or another scenario might be that somewhere west of our sample site, there was a fault that uplifted the Olympics relative to the Puget Lowland. And if you think of that happening in the context of an earthquake being a sudden event, but the larger tectonic movements continuing before and after, the Olympics would gradually keep rising, the Puget Lowland would gradually keep dropping, and the earthquake would simply relieve some of the stress between those two opposite movements. So if there's a fault that does that west of our sample site, it would move the river down in the lower portion, and it would lower the river gradient in the lower portion of the Dosewallips between the fault and the shore. And that alone could be enough to where we suddenly get an aggradation of the lower valley floor. I'm not sure how big an earthquake and where that would have been, and whether it would have propagated far enough upstream to our sample site, but it's a scenario that I don't know enough to dismiss offhand. Suffice to say that there's a couple of different ways you can look at this record of Holocene aggradation and valley scouring again, and in terms of sort of your interest of valley dynamics management, every once in a while we get sizable geologic disturbances that would really mess with the system in a major way. And I guess that's where I can stop. If there's any questions, if anybody's still there, I guess there's still some people. I know some of you have had to sign off. I'll be happy to stick around for questions. I also have a few more pretty pictures that I can stroll through if anybody wants, but not so much specific geology to talk about anymore, just nice pictures of rocks and rivers that we bumped into while we were mapping in the neighborhood.
I would thank you so much. I just wondered, the Dosewallips River Valley itself, does that seem to coincide with faulting, or would just have any thoughts on
Well,
the fact that we have like the Dosey duck and Hamma Hamma all parallel to one, excuse me.
Yeah, so I'm gonna end the slideshow, and now you can see my notes again, right? Is that correct? Okay. So if you look at that broader map, or actually, let me go down a little bit. If you look at that broader map of the Olympics, you know, the black lines here are the faults that have been mapped as through-going features. So that's where geologists have found, okay, there's a fault in the sort of central Dosewallips River basin. There's one in the upper Dosewallips River basin. Both of these are where the east side is riding up over top of the west side. So those on the face of it wouldn't necessarily do what we're seeing in that particular exposure. But when you think about what happens as you lift the Olympics up, if this is the Olympics and these are rock layers up against the Olympics, as the Olympics rise, those rock layers are going to get folded up. And that's going to cause a little bit of sliding and stress. So an earthquake might happen when these keep moving and there's an increasing amount of tension, and then it snaps. So these faults that you're seeing here are that kind of snap. If you go a little bit farther east, you still have that same sort of east-west compression, but it's not necessarily a given that you have the same kind of offset. Maybe what you have, if this is the surface and here's a fault that comes up, maybe you get that kind of offset, which would still move the Olympics up against the Puget Lowland, and it would then lower the gradient in the Dosewallips River that runs from west to east across here. Is that making sense? Did I lose you? The long and the short of it is we don't know specifically which fault or if a known fault would have been responsible for this if this was a fault effect. But I could see this kind of signal coming out of a fault effect, which is why I mentioned it as one possibility. But it's not the only possibility. A landslide could have happened too. I don't necessarily see in this particular setting where I would point to a likely landslide that would have done that, with a possible exception of right here. There's that little stretch of the river that forms a steeply incised bedrock gorge, much like that, and it might have actually been that picture I showed early on here. I know that that stretch of the river looks a lot like that. What we didn't find in that particular location is a source that we could point to for something coming down from the slopes and blocking the river that way. There just wasn't a hollow tooth big enough to give us enough rock to dam the river and bring that level up enough. So I didn't particularly like the notion of a landslide doing this. And I didn't have a very good specific rationale to blame it on faulting. And then there was that thing about a somewhat similar age coming out of somewhat similar deposit farther upstream that Garcia had found farther west from our map area. So we want to consider the possibility that maybe it's just a fine sediment pulse that was related to a big fire somewhere in the Olympics. And we know from the fire history in the Olympics that big fires are rare, but when they happen, they are monsters, or they can be. Every few hundred or few thousand years, it seems like there's some massive fire that goes through parts of the Olympics, and that's how, as I understand it, the ecologists tell us the high mountain prairies in the Olympics tend to form. So when you get a fire that is so fierce that it burns hundreds of square miles all at once and denudes the forest, you're gonna get a lot of post-fire sediment washing down into the basin. And that could really clog up the system for a few hundred years, or at least a few decades. So that certainly is one possibility, and the abundance of charcoal in our deposit went with it rather nicely.
Michael?
Yes.
This is Joseph. How does your work bear on the geomorphology and fish habitat?
How does my work affect the geomorphology and fish habitat?
Bear on, not affect.
Or bear on. Right. Not very much directly. I want to say that maybe it gives us a rationale to think that perhaps the water in the Dosewallips is relatively nutrient poor, because most of the rock going into it is relatively unweathered. Not that that would be a whole lot different from pretty much all of the Puget Lowland river systems, to the extent that glaciers scoured out the landscape repeatedly throughout the Pleistocene, and most recently 20,000 years ago in the case of northern sourced ice, and perhaps more recently with alpine ice. Yeah, all of that would have sent sediment pulses down the slopes at the time, and it would have scoured the surface to where rotten rock probably is not there anymore, or not much. And what we now have available for erosion is relatively unweathered rock, so nutrients don't get flushed into the water quite as easily as they might otherwise in an unglaciated terrain like south of Tenino. That's just one thought.
That
yeah.
seems very significant.
Well, yes, but it's also out of my wheelhouse a little bit.
Okay.
I just kind of want to throw out, okay, we don't get enough time in the system since the last glaciation for there to be a lot of deep weathering. We find deeply weathered rocks above 3,000 feet, but in terms of the volumetric contribution into the rivers, that's probably not that much. So I just don't see a good pathway for generating all that much nutrient for these waters. Again, not something different from other Puget Lowland drainages, but just one of the attributes of what we get in these glaciated terrains of Western Washington.
Thank you.
You bet.
Are there any other questions for Michael?
Hey, Michael, this is Scott. I have a question for you. That was a great talk. Thank you so much for that one. So you mentioned that from the Pleistocene to the mid 20th century, that the glaciation in the Olympics appears to be driven more by temperature rather than precipitation.
Yeah.
And I'm wondering if you or others have noticed a kind of a shift in that trend with the recent rapidly warming climate, or do we feel like the glaciers, particularly those west side glaciers and the ones that influence the Dosewallips at the crest, are being more controlled by temperature changes rather than just simply precipitation?
That is a good question, and I've sort of thought about that too. If you look at these studies of ice in the Olympics nowadays, the part that makes me wonder where we're going with this is that you really need to look in the uppermost elevations of the Olympics now to find any ice. If you warm the place up by much more, you're simply not going to get any ice forming, no matter how much precipitation there is, just because it's too warm to form ice. So I don't quite know what to predict there, but it may very well be that we're heading out of the ice ages for the Olympics. I don't know how much of a temperature change it's going to take for us to run out of the existing ice, but it seems like historically the ice volume in the Olympics has decreased markedly. It's not something that I've tracked specifically, but it seems like people who care about it keeps telling us that yes, there's less ice over the decades in the Olympics, and that certainly seems in line with the global trend. Who knows what this climatic shift is going to do to the jet stream, and if that might make a difference. At this point, we get most of our precipitation in the winter, and the average of that is that we still need to be at somewhere above 1,500 meters to get any of that really forming ice, enough to where it builds a glacier. It's not going to take a whole lot of warming for that to shift above the top of the Olympics, really. So I think we might be teetering on that one. Again, a little bit out of my wheelhouse, but that's as far as I'm willing to speculate.
Thanks.
Are there any other questions? I know one person was interested in the studies that you've mentioned and other references, and wonders.
Yeah, I see in the chats there's something great stuff. Can we get the thesis and papers here mentioned? Was that about every publication I referenced, or was that a specific one?
Maybe the master's thesis in particular?
There was a couple of those, but fair enough.
Sure.
So what I can do is those, well, for one thing, I can put an email to you together, Tammy, that lists the particular theses or papers that I mentioned. And for at least some of these, I can either attach those to the email or I can put them on an FTP site. I don't know that I have all of these available electronically, and if I don't, at this point, I can't send copies to everybody out of our library. I'm pretty sure that every one of the things I cited is available in the Washington Geological Library, at least as a paper copy. And if somebody really wants it at this time, they should be able to get our librarian to either loan them the paper copy or maybe coax them into scanning it and sending them the electronic copy. So why don't I put together an email that at least gives you the references and either attaches what I have or puts it on the FTP site so you can download it and you can distribute that among the audience here.
That would be wonderful. I'm just curious, and you're looking at all the organic material. Are you encountering any fish remains of any kind, or is it unusual?
The only fish remains that I'm specifically aware of, having played into the geology or the geologic mapping of the Olympic Peninsula, are at the are in the Skokomish River Valley. There is a particular location in the, I think it was the South Fork Skokomish River. So here's the North Fork, here's the South Fork, and I want to say someplace in this stretch of the South Fork, there was a locale where a bunch of silt washed into an old lake, and it was gravel and silt. It was a bit of a foreset deposit, I think. So it was kind of a delta like what we had shown, only at a smaller scale, if I remember this right. And for whatever reason, there's an accumulation of salmonids that got washed in and fossilized in place. And I want to say about 45 years ago or so, somebody sampled that. This was on private forest land, and it was at the time, I think that was Simpson timber. Is it Simpson?
Yeah.
It was one of the forestry outfits in Shelton that still has a fossil specimen from in their office in Shelton. But anyway, the salmonid fossil was studied in terms of its bone structure and attributes, and it seemed to point to something that was tied to the Chehalis River rather than things farther north in the Puget Lowland. And it was inferred partly on account of the biology and partly on account of an assumption that an ash deposit associated with this fish burial ground is the same ash as was found elsewhere in the neighborhood of Southern Hood Canal around here. That particular ash ended up being, I think it was 0.83 million years old.
Yeah.
So we have a record, if that correlation holds, of one of the oldest ice deposits that's actually got some age control associated with it anywhere in the Puget Lowland. And in this case, periglacial conditions that seemed to allow these fish to either survive in a refugium that was cut off from the outside world at the time, or migrate via the Chehalis up and down into the Olympics. That's the only fish story I know of in that context. Not to say that we shouldn't keep looking. I think we should, and it wouldn't be out of the question that instead of bits of charcoal, or in our case, what we actually dated was little coniferous needle bits. If we find good fish bones, we can radiocarbon date those too. Fish are a little bit more complex than pine needles, in the sense that it may matter, depending on the species and the environment, what part of the fish you send out for radiocarbon, and whether or not that fish was exposed somewhere during its lifetime to marine conditions, i.e. salt water. All of those things could affect the radiocarbon age, or the numeric result. So that might be a little bit more complex in terms of putting the right age on it.
Just have to find more of them, perhaps.
Yep.
Well, thank you so much. It was really wonderful to hear what you had to say and get a better picture of the bigger context.
Well, I hope it helps the group. I know it's a little bit off topic for most of the focus of the group,